Thank you. Let's begin with a word of prayer. Dear Heavenly Father, we thank you for this morning. We thank you for your grace and mercy for us each and every day, Lord. I just pray to be with us this morning. Help us to, again, Lord, glorify you in what we do. And I also pray that you encourage the students if they had a bad day yesterday to persevere. And in my prayer, Lord Jesus. Amen. I don't know yet because I haven't started grading. I got wrapped up in a puzzle yesterday I could not solve. And so not exactly a mathematical puzzle, although it was about math. So, all right. So we're talking about differential equations. So basically, the next 3 lectures I'll spend in here talking to you about the essential, I guess you could say, most famous elementary differential equations which we can solve with fairly little effort. And well, the truth is that the techniques I'll show you in the next 3 days actually solve the lion's share of problems that you'll come across in introductory courses, which is why we put this here. You're like, but then we have a separate course in differential equations. Well, yeah, but if you follow along these next 3 lectures, you'll be able to solve, I don't know, in my experience, about 90% of the problems that present themselves in usual applications of science and so forth. All right, so the first thing is, what is a differential equation? Well, it's kind of what it sounds like. It's an equation that involves derivatives. So that's not especially enlightening. Here's an example of one. You're trying to solve the integral, right, of, let's say, little f of x dx is equal to y. You're like, but isn't that, so, you know, you're for a given. Right, for a given f of x. So, for example, you're trying to say integrate e to the x dx, right? So you know what y is equal to. Y is equal to what? What's the integral of e to the x dx? It's what? Right, e to the x plus c. All right, so you're like, okay, well, you just told me a differential equation is an equation involving derivatives. I don't see any derivatives, right? Fair enough, fair enough. Let me show you the corresponding differential equation here. And it's, in some sense, just a matter of notation, right? But the corresponding differential equation here is dy dx is equal to f of x. All right? That and that are the same animal. So you've already been solving differential equations this whole semester. Every time you do an integration, you're solving a corresponding differential equation of a very specific and special type, but a differential equation nonetheless. So don't be scared of differential equations. Differential equations really are nothing more than weirdly written integrals. All right? So this is a differential equation. This has general solution right here. All right, so this differential equation we could solve basically by integration is the point. We already have a process for solving that kind of differential equation. But you can look at a much more general class of differential equations. So generically speaking, and this will be a somewhat sketchy definition, but if you have a function of 2 variables, really, well, maybe 3, let's say x, y, and y prime equals to 0, all right, then this is a first-order differential equation. All right. It's also called an ordinary differential equation. Ordinary differential equation. Or short, you'll hear people say this, it's an ODE. And the reason that this is an ODE, for example, that's an ODE, is there's just one independent variable. That's all we'll solve in calculus 2 because we don't know calculus of several variables, right? That's next semester. So ODEs is what we'll solve in here. We'll solve first order ODEs. And what would a second order differential equation? So there's lots of different examples of this. Let me just show you a few. dy dx. Of course, the one we already did, like dy dx equals to, say, tangent x. There's an ODE. Another one, how about this? dy dx squared plus y is equal to sine of x. There's an ODE. Yes, sir?
What do you mean by first order equation?
It is some function of x, y, and y prime. It's an equation that involves, now you could be more technical, right? I mean, it has to involve the first derivative in a non-trivial sense. All of these two examples I've written down so far illustrate what is meant by non-trivial appearance of the first derivative. But I will grant you, to give a careful definition of that would take us far afield. So I'm just trying to give you some language here. Not like Trump, but all right. So dy dx plus xy is equal to e to the x squared. There is another first order differential equation. All right. We can solve, okay, here's another. Dy dx is equal to x times y. Again, a first order differential equation. All right. All right. What would not be a first order differential equation? How about this? Y prime prime plus y equals to 0. This would be where y prime prime is notation for d squared y dx squared. This would be a what? Second order differential equation. Now, all the differential equations I wrote here are linear except for one. A differential equation is said to be a linear differential equation if y and y prime and higher derivatives appear linearly. So linear ODE has y prime, etc. appearing linearly. What do I mean by appearing linearly? That's kind of an intuitive term. But what I mean by that is that you don't have terms like dy dx squared, right? Or here's another thing that would be nonlinear. For example, y prime plus sine of y is equal to 0. That's a first order nonlinear differential equation, highly nonlinear. All right. So I'm just trying to give you a lay of the land here for a couple minutes. It's some terminology. Yep.
ODE is assumed as first order?
Not necessarily. ODE could be second order, third order.
Oh, okay.
So a linear ODE has, out to the nth derivative is nth order ODE, nth order linear ODE. Now the reason I'm telling you these things is I just want to kind of give you the big picture, and then I'll start working problems here very shortly. We can solve linear ODEs, all right? There exist machines to dispatch these with relative ease, with calculus that you already know. So we essentially own linear ODEs. We can send them to their maker. No big deal. Nonlinear differential equations. That's another ballgame. That's not something that I can explain to you how to solve. And I don't think it's something that anybody really has a well-developed general theory of how to solve. So for nonlinear ODEs, we have to resort to qualitative analysis, which we'll get some into in the ODE course. Actually, our differential equations course is part ODE, part PDE in principle, although some semesters it may just be ODE. All right, enough. So that's just some general terminology. So what we're talking about today is a specific corner of this, right? So what we're going to look at is the problem of, it's a very specific problem. We're going to look at how to solve linear first order ODEs. So the problem we're facing mathematically is this. How do you solve for a given, let's say, P and Q? So these we're going to assume are continuous functions of x. We want to solve the following problem. We want to solve dy dx plus py is equal to q. So what I've just put here for you guys is a so-called linear differential equation in its so-called standard form, I think. Different books have different standards for what's quote-unquote standard form. Some people would call it normal form. I don't remember what your book does. I'm trying to use the same letters as your book as to not overwhelm you with more alphabet soup. Sorry to be so boring. Let's see here. Does he give a name? Oh, I'm sorry. He uses lowercase p and lowercase q. Can you forgive me? I'm going to continue using my capital P and Q. Anyway, mind your P's and Q's. Let's see here. Oh, I'm sorry. I don't think that has a sting anymore. I think no one knows this expression anymore. It used to be a very popular expression. You know? Show of hands, who's ever heard mind your P's and Q's before? Oh, okay. So still about half of you? No. The half of you who will... What's that? Mind your P's and Q's. Have you ever heard this expression? No? Here's a more useful thing. Who has not heard it before me just saying it? You don't know what it means? Yeah, that's a good question. What? I know it means mind your manners, but why? This is a very dangerous thing. Whenever you're thinking about some colloquialism, there's a chance that it's something awful. So you shouldn't go into this blindly trying to figure out what an abbreviation means. It could be bad. All right, so I'm going to leave it to go. I'm going to let it go. I mean, for example, there's an annoying thing. My grandparents, they have both gone to be with the Lord now, but every time I talk about physics, they just start giggling. I was like, what? Apparently, I don't know, it has something to do with digestion for their generation. There's some, I mean, this term is out of use now. I don't know. So you never know. All right. I obviously needed to drink more coffee before today, or maybe less, I'm not sure. The Goldilocks problem of coffee. What exactly is the right amount before class? So dy dx plus py, we would like to solve this. Now, for example, let me just show you some token examples of this before I even do it. So for example, you might want to solve dy dx plus xy is equal to x squared. Or you might want to solve, you might want to try to solve something like x squared dy dx plus x cubed y equals to x to the fourth. So, I mean, the first thing I'm trying to tell you is in order to use the method I'm about to show you, the machine I'm about to build, we first have to put the differential equation into its proper form, right? Its proper form, this in the green so-called standard form. All right. So are these different differential equations? How would you tell if two differential equations were the same or not? How would you tell if two different regular equations were the same or not? If two equations are the same, what should we insist about? How can we measure that sameness? Here, for example, is x equals to 1 and is x squared equals to 1 the same equation? I just squared both sides, right? What's the difference? Here's how I would measure it. The solution set of this, what? Is just 1, right? What's the solution set here? Right, -1, 1. So these have different solution sets, so clearly they're not the same equation. So you could measure the sameness of differential equations in the same way. If two differential equations are the same equation, same differential equation, surely they should have the same solution set. But what does the solution set for a differential equation look like? Well, so like this example, the solution set was what? E to the x plus c such that c is a real number. Whoa, that's big. Infinitely many functions, right? So a differential equation has a much larger kind of solution set than an algebraic equation. That's not too surprising, really. All right, so how do you get from here from my example 2 to my example 1. Right, just if we just divide by x squared, right? Then we get back up to there. Or alternatively, you can multiply this one by x squared to get down here. So, and then I guess the question is, do we lose anything by dividing, is x equal to 0? Are we losing x equal to 0? Well, I suppose in here we'll just look at solutions which are functions, at least for the moment. So x equal to 0 isn't something to lose. All right. So here's the technique. And so what we do is we introduce this thing called h. Now h of x is equal to the integral of the exponential of, oh, I'm sorry. I've got my integration and exponentiation out of order. Other way around. It's the exponential of the integral of that coefficient p dx. This is the so-called integrating factor. That's its name. All right. Now, you can ask, what? Why? That's bizarre. I've never done something like that before. These are valid thoughts to have. And the answer for why we're doing this is probably a little bit outside our grasp. I mean, the best answer I can give you at the moment is just wait a minute and you'll see what it does for you. Where this is coming from mathematically is a little bit deeper. Now, so what can we do though? What's the derivative of h here? If I calculate dh dx, what do I get? So this is just notation for e to the integral, all right? Don't be confused by my notation. So how do you differentiate an exponential? Mm-hmm. Oh, no, you're thinking power function. So, yeah, we just, derivative of e to the x is just e to the x again, but if we're differentiating e to the u, we have like e to the u times du dx, right? In this case, u is equal to the integral of p dx, right? So I have to do e to the integral of p dx times derivative with respect to x of p dx, okay? Sorry, sometimes I write the of x dependence, and sometimes I don't, and it's not, there's no secret hidden logic behind why I'm omitting it sometimes and making it explicit other times. It's just, I guess the x has a cloaking mechanism and it's sometimes failing. Whatever you want. Okay, so what's the derivative of the integral of p dx? P, right. So check this out. So this is P. What's this? It's H again, right? So what we get is this wonderful little identity, which is the derivative of the integrating factor is P times the integrating factor once more. All right? So this is an identity that we're going to use. So this standard form, let's give it a name. Let's call it star. And let's call this, let's just give this a name too. Let's say that dh dx equals to p. Let's give this a label, ph. Let's call this star star. Okay. So my next move here is going to be to multiply star by the integrating factor. All right? So if we say h times dy dx plus ph times y, it's equal to qh. So multiplying star by the integrating factor h. Question. Is that dangerous? You know, if I multiply an equation by 0, I lose all information about it, right? Is this integrating factor ever 0? It's the exponential of something, right? What do we know about exponentials? Right, they can never be, they're positive, right? I mean, so totally safe. Haven't lost anything. And then, and here is the real reason for integrating, for inventing this integrating factor, is it brings to bear this reverse product rule. Look at this. What you have then is h times dy dx, right? Plus what? dh dx times y is equal to qh by star star. See, because pH is exactly dh dx. That is so very nice. So now, this is the derivative with respect to x of the integrating factor times y is equal to qh. And now, let me call this star star star. Now that we have reached the triple star, see, we're back to the sort of thing we started with, right? We have the derivative of something is equal to another given thing. So how do we solve that triple star equation? You know? No? I thought I saw understanding. Somebody take a guess. How do we solve triple star? Integrate, yeah. Exactly. So natural enemy of the derivative is the integral. So integrate both sides of triple star. And we get hy is equal to the integral q of h dx. And hence y is equal to 1 over h, the integral of q h dx. And so there you go, where h is defined by the exponential of the integral p dx. That thing we just did, this argument we just did, solves arbitrary linear first order ODEs for a given p and q. Yep.
When you are saying let's solve for the third star, for example, I don't know exactly.
Well, I'm trying to find y. I'm trying to find a solution, right? Yeah. So the point of this is I found an explicit solution. So this is an explicit solution. It might not seem very explicit, but explicit solution, the classical language is in terms of quadratures, which is just a fancy way for saying it's an integral solution. Sorry, I'm not going to write that. It's an integral solution, explicit integral solution. An integral solution is one that involves integrals of dy dx plus py equals to q. Now, some of you will get the wrong idea from this, perhaps, which would be that, you know, we're just going to use this formula. It's just a plug and chug black box. We just put in the p and the q and work out the formula. That is not what I want to tell you. Actually, what we're going to do as we solve problems is we're going to go back through this proof of the technique each time. If we do this, it builds in a redundancy to the calculation. Let me show you how this works. So what I'm going to do now is do the same argument for a specific example, and you'll see how it all works out. So here's a specific example. You're like, well, finally. Okay. How about this? Dy dx plus xy is equal to, oh, I don't know. Put a 1 over here, see if we can do that. Wouldn't be my luck to. So in this case, we have what? P is just equal to x, right? Q is equal to 1. All right, so first order of business, h is the exponential of the integral of x dx in this case. which is what? One half x squared. By the way, you say, well, why don't you add a constant, right? If I was to add a constant here, all I would do is effectively put a multiplicative, it would put a multiplier. You know, what happens if you add a constant to an exponential? Like if I do this plus a c, it just adds like a multiplier here, right? Because if I add, plus a c, what do I get? Right? And so if you look at where you're going with this, eventually you're going to divide by exponential, so that exponential c term would just cancel out when you get to the final step. So without loss of generality, we can just not add the constant for the integration of p. So I don't do that, right? So I don't have to add plus c. I just say 1 half x squared. I know that will work because I know where I'm going. What's our next move? Let me number them. So number 1 was to calculate the integrating factor. Number 2 is to multiply the differential equation, which is given to us in standard form. All right, so I'm going to have e to the 1 half x squared dy dx plus x e to the 1 half x squared y is equal to e to the 1 half x squared. Like that. I just multiply the given differential equation by the integrating factor. Then what? If, and here's the big if you calculated the integrating factor correctly, right? If you calculated the integrating factor correctly, then this will happen. The reverse product rule will happen. If you didn't calculate the integrating factor correctly, this step right here in the calculation will show you that. So it's very important to work through this, to really think through this step. Is this in fact d dx of e to the 1 half x squared times y? So what do you guys think? Did I calculate the integrating factor correctly? Did it work? Try it out. Differentiate e to the 1 half x squared. What do you get? E to the 1 half x squared times what? Times x, right? Which is what we have in the step above, right? And then the other term, of course, is dy dx by the product rule. Right? Then what? So step 4 is up here, which was to integrate both sides. We have then e to the 1 half x squared. Y is equal to the integral of e to the 1 half x squared dx. Yeah, that's not an integral I can do. Well, I could do it with power series, which we'll get to in a few weeks, but at the moment, there's no elementary way to integrate that, all right? So there you have it. And then we solve for y to get the explicit solution. That's step 5. Y is equal to, 1 over e to the 1 half x squared, the integral of e to the 1 half x squared dx. And there you go. That is an integral solution to the given differential equation. It's weird the first time you see it. After I do it again, you'll start to get bored. Yeah.
Why didn't we take the derivative?
Because we don't need to.
Oh, so we don't need dh dx equals ph.
I mean, and I did that in my thinking. That's implicit going from step 2 to step 3. I don't think there's a need to write it. I mean, what I'm saying is I would do that. That's differentiation, so I don't require you to write that down. I mean, you can, there's a thought bubble here. Yeah. But If you burst the bubble, then you've removed the error checking part of my algorithm here, right? When I teach DEqs, I have a certain subclass of students who just go through this blindly without actually checking that step 2 and 3 are legitimately connected. And so for those students, they might as well just use the boxed formula. See, the boxed formula has no error check in it, right? You just would, I mean, of course, look at this. I mean, what we found in the end, right, is exactly this, right? With h equal to what it is in this problem. Okay, so let's look at an example. I'll do one more mathematical example, then I'll tell you guys about some physical problems. Let's see here. So let me try to make up one that's a little bit more interesting. Yeah, I'll do example 3 in the book. It's a good one. So xy prime minus 2y equals 3x to the 4th. I already forgot it. What did I say? Minus 2y, golly, equals 3x to the 4th. And we're also given something here. We're given additional piece of information. In particular, we are given this condition that y of minus 2 is equal to 2. Did I say? Minus 1 is equal to 2. Y of minus 1 is equal to 2. I knew it. All right. So what I just found in our previous example is the so-called general solution, right? That doesn't, that includes all possible solutions according to the It's like, I guess they're not ending. He's just putting away the, it's like, doesn't seem like it's the end of class yet. All right, so first of all, this is not yet in the form we want, right? First of all, there's a step 0. Step 0 is to put it in the box. So we got to put it in standard form. How do you do that? This one. Just divide by x, right? Then what? Identify the p, right? What is p in this problem? P is minus 2 over x, right? Hence, the integrating factor h will be the exponential of the integral of minus 2 dx over x. So what's the integral of minus 2 over x? It's minus 2 natural log of x, right? Absolute value of x, to be careful. There's no reason to assume that x is positive or negative here. In fact, apparently the condition we're looking for has an x negative. So we better be careful about the absolute value. And that I can't, this is not equal to minus 2 natural log of x, by the way, right? That's not how the simplification goes here. We have to do what? We have to bring this power inside the logarithm before we can simplify. So what is that? That's exponential of the log of the absolute value of x to the minus 2 power, right, by properties of logarithms. And this is what? This is the exponential of the natural log of 1 over the absolute value of x. Oh, I'm sorry. Why don't I just get to the point here before I mean, stop writing the exponential and log. We don't need to do that anymore, obviously, right? Okay, so now I can cancel them as their inverse functions, and I have the absolute value of x to the minus 2 power, right? Which is really 1 over absolute value of x squared, which is what? Absolute value of x squared. Can you simplify that? It's just x squared, right? Because if x is positive, absolute value of x is x. If x is negative, absolute value of x is minus x. Either way you square it, it squares to x squared. So alternatively, of course, you could recall that the absolute value of x is the square root of x squared. So if we square both sides, we get this. All right. Whatever floats your boat. Anyway, there is the integrating factor. So now what do we do? Multiply this differential equation. Let me give it a name. I'll call it star. Multiply star by our integrating factor h is 1 over x squared. All right, so what's that give us? That gives me 1 over x squared, y prime, minus 2 over x cubed, y is equal to 3x. Now, okay, so let's think through this. Is this, in fact, the derivative with respect to x of what? 1 over x squared times y. Is that valid? What's the derivative of 1 over x squared? Right, minus 2 over x cubed, which is what we have right up here, thanks to the conniving of the integrating factor, right? So we get reverse product rule. This is equal to 3x. And then we do what? We want to solve for y. Integrate both sides. We can do that, right? So integrating gives me 1 over x squared times y is equal to 3/2 x squared plus a constant. It's important to add the constant right here because that's where you integrated. The plus a constant is implicit within the boxed formula of the previous example. It's hard to see in there. All right? Now solve for y, and we get y is equal to 3/2 x to the 4th plus cx squared. So I'll put it in a box here for a second. This is not the answer to the given question, but what I've just boxed is the general solution to the differential equation. What's the general solution to a differential equation? What that means, it's much like what's the indefinite integral. The indefinite integral is the general solution to the problem dy dx equals to f. Technically speaking, the indefinite integral is really a set of functions, right? I mean, it would be more accurate to write this. No one writes this, right? But it would actually be more honest to write this. See, because the indefinite integral, it's not just one antiderivative, it's the idea that it has captured all possible antiderivatives. Really, it's the solution set, the general solution set. This is, in fact, the solution set to dy dx equals to x squared. It's the general, it's all possible solutions. So what is the general solution? Another way to look at it is the general solution includes how you would respond to any given initial condition. Every possible initial condition you can conceive of, the general solution will address. All right? So anyway, that's the general solution. You notice this is really different, right? Your general solutions before, it's always just like function plus a constant. So if you look at them graphically, how are they related? Just vertical translation, right? The antiderivatives are all just vertical shifts. How are different members of this family of functions related? Not nicely. I mean, the solutions to differential equations can be all kinds of weirdo, just bizarre shapes. But they tend to like foliate the plane. Like there would be well, anyway. I won't try to do that. So we're not done yet. What do we have to do to answer the question? What do we need? We need to find the specific solution that solves y of minus 1 equal to 2. So what do I do now? Right, so I put 2 is equal to what? Plug it into the formula, like 3/2 minus 1 to the 4th power plus c times minus 1 squared. And that should tell us what the appropriate choice of c is, which is what? So the specific solution which solves the given initial value problem. An initial value problem is just a differential equation paired with a set of initial data, like this problem. There it is. Oh, I was like, something seemed too easy. Yes, thank you. Very good. Keep me honest. Very good, very good. I probably buried the lead at this point. Maybe you guys would want to know where differential equations come up in daily life and such. By the way, the book might have 2 or 3 examples in the section, right? If you look at my website and if you look at the posted notes, I've got at least a dozen examples of these. I have oodles I have many, many, many examples. So if you didn't get the idea from these 2 examples, there are many, many more to look at. But I'm going to just change gears here a little bit and just talk about some places where differential equations come up, right? So let's see here. Population growth. So this naive population growth is something like this. dp dt is equal to kp, something like that. So that says that the growth rate of the population is proportional to what? The amount of population is actually there. So here k would be a what? Well, usually, I mean, you take k greater than 0. You can talk about radioactive decay. So you can talk about the number of particles. And the number of particles, you could say, I don't know, like, well, I guess it's a question of notation. I'm going to say minus r, n, where r is greater than 0, which is, so, I don't know, maybe you've got a kilogram of some mysterious substance called polonium, and it's unstable, right? And after about 2 weeks, it decays into whatever's in the fridge close to my office. It's not a good smell. I don't know what its smell is, but there's a smell. And how can freezers smell like that? I don't know, but it does. It's been there since, like, I came back from break and I was like, whoa, no, that is wrong. See, there was decay. Something decayed. And decay is basically your milk going bad. There's a certain number of, bacteria, and the growth is this kind of exponential growth. It starts out small, but it gets bigger. This, on the other hand, is exponential decay. That's just a choice of sign. You can talk about Newton's law of cooling. What's Newton's law of cooling say? So like dt, big T is the temperature, little t is time. So we talk about some object, I don't know, like a cup of coffee as usual, right? And you got some coffee in here. And then out here you've got air, right? And so as you know what happens, if you have a hot cup of coffee, what does it do? It cools, right? How fast does it cool? That depends on the temperature differential, right? The larger difference there is between the temperature of the coffee and the temperature of the air, the faster it cools. Well, that's actually Newton's law of cooling. It says that the change in the temperature rate of change is proportional to the temperature minus some ambient temperature. We could call it, I'll call it R for room temperature. So here, K and R are constants. And I think I don't know, if you want K to be positive, I guess I need to put a minus in here. What do you guys want? Do you want K to be positive or negative? It's up to you. Positive, all right, then I need a minus in order for this to make sense, because certainly if T is greater than R, just think about the cases. If T is greater than R, what's that mean? Minus K times t minus r is what? Less than 0, right? If k is greater than 0. See, because I'd have a negative times a positive, which is negative. And that makes sense, right? If the temperature of the coffee is larger than the room temperature, it should decrease. Okay? And vice versa, if the temperature of the coffee is less than room temperature, that implies that this term is greater than 0, right? For example, you have iced coffee, right? It will raise to room temperature after a little bit. And that's the Newton's law of cooling, which is very easy to express, right? We've decided that to be the case. But you could easily see that I could rewrite this silly equation as like, what? I could rewrite this as like AT plus B, where A and B are just, combinations of the things I have there. Now, Newton's law of cooling is really different than the first two examples I have there because it involves two constants, right? This cooling coefficient as well as the ambient temperature. So if you want to solve a Newton's law of cooling problem, you need two pieces of data. Whereas one of these guys, like population growth or radioactive decay, like one piece of data will allow you to find a solution. There's another kind of population decay, population growth rather, population decay, listen to me. We may be experiencing that right now societally. But there's a population growth with carrying capacity. Carrying capacity, so that's something like this, dp dt is equal to something like kp times 1 minus, let me see if I get this right, I think p over c, if I remember right. So I multiplied just exponential population growth, right, by what? By this factor 1 minus p over c. What happens with this extra multiplier what happens when p is equal to c? Right, the growth rate 0. And what happens if p is what? If p is larger than c, what happens to the growth rate? Like if this is 2c, this whole thing is minus 1, right? So the growth rate is negative if the population is larger than the carrying capacity. Whereas the growth rate is positive if the population is less than the capacity. However, it's attenuated as the population, say, reaches that carrying capacity. So maybe you've got like a pond and you're talking about like fish in a pond. It can only stock 10,000 fish, right? So if you have like 15,000, 5,000 of them are going to die. It'll eventually go back to 10,000 because that's all it can sustain. Or maybe bacteria in a petri dish or something is a better example. It's fun to read differential equations books from like the 1940s. They'll talk about the carrying capacity of the U.S. and they'll say like 200 million. It's like, yeah, oops, you're wrong. And that's kind of the history of population growth. It's like you can write down some equation, but the thing is, history is replete with unexpected technologies and events and so forth. You can't really model human population growth. I don't think anyway. Anyway, so here's some, and there's other ones, right? Like if you look at an RC circuit. Do you guys know RC circuits? One of these guys. Or if you look at an LC circuit, well. Anyway, so all the basic circuits with inductors or capacitors, these also lead to first order differential equations. But anyway, tomorrow I may work another example of this, but then we'll work the other major technique, which is separation of variables. That's much easier in terms of like theoretical burden. The separation of variables, that almost sells it for what it is. You separate variables and you integrate, and that's kind of it. There's a little bit more theory in your book, which I'll talk about, but that's kind of it. We can go through the solutions to these tomorrow. Thanks, guys.